Today we're going to be discussing the concept of density. Now, density is a reasonably important concept in and of itself. Density is something that students are expected to know something about. But we actually have a more important goal today. We're trying to lay the foundation for the entire remainder of this course. We are trying to get you to a point where you deeply understand the fundamental quantities discussed in chemistry and their more common and fundamental relationships. And density provides us with an excellent vehicle with which to start this process. It is very possible that you have, quote, learned or had this concept discussed at one point or another in your scientific education. When I ask my students what density is, the most common answer I get is density equals mass over volume, or they'll say D equals M over V. Now that's fine because it certainly is correct. But let's take another look at that. Does saying that D equals M over V prove that this has any real meaning? Well, I would argue that while it certainly could have meaning to any particular student, just being able to recite that formula doesn't prove that it does. Let me illustrate why. Suppose I wanted to present another concept solely by presenting a formula. Tremdifts equals min-fats over ring-bats. Now I could say, now you listen to me because I'm the teacher and I want you to know about tremdifts, min-fats, and ring-bats. And tremdifts equals min-fats over ring-bats. And I'll give you a formula. T equals M over R. And tomorrow we're going to have a quiz on this. And on this quiz I will tell you T and I will tell you M and you will have to solve for R. Or maybe I'll tell you M and R and you will have to solve for T, or maybe I'll give you T and R and you'll have to solve for M. We could even make story problems out of this. If you have 5.77 min-fats of Flibbeldorf and the tremdifts of Flibbeldorf is equal to 8.32 min-fats per ring-bat, then how many ring-bats of Flibbeldorf do you have? There's a good chance that you do well on the first three problems, assuming you can manipulate the algebraic equation T equals M over R correctly. Now, I may have confused you with the last problem because I introduced that new term Flibbeldorf. So we might have to learn how to translate the terms in this kind of problem so we could line them up with the T, M, and R before we would get really good at doing these kind of story problems as well. But let's suppose that we took the time to work at this until you could get 100% on a tremdifts, min-fats, and ring-bats exam. That's great. You'd feel good, and I, as your teacher, would feel good also because you did so well on the exam. But the question I have to ask is, what do you really know and understand about tremdifts, min-fats, and ring-bats? I think the answer for the most part is almost nothing because there is no meaning here. And that's the point. Saying that D equals M over V isn't bad. It's true, and it's good, but it doesn't prove that you understand anything about the concept of density. Now you might ask, well, why do we have to understand the concept anyway? After all, if I know that D equals M over V and I can solve the problems, isn't that good enough? And in one sense, I suppose you could say it is. But in another sense, it isn't. And here's why. Density involves two quantities and one relationship. The quantities are mass and volume, perhaps measured in grams and cubic centimeters. And the relationship is a number of grams that are contained in 1 cubic centimeter. Now, do you think that density is the only time in chemistry that you're going to encounter the concept of mass and the units of grams? Do you think that density is the only time in the course that you're going to encounter the concept of volume and the units of cubic centimeters? Of course not. And do you think that density is the only concept that will involve a this per that? Again, certainly not. So we can use density as a vehicle to help us understand some of the fundamental quantities that are going to come up again and again and again throughout the entire course. There's also another weakness to just memorizing a formula. What if I ask you a question like, which occupies a larger volume, 5 grams of lead or 5 grams of styrofoam? Now, if you don't understand the concept of density, If all you've done is memorize a formula, you're going to have a difficult time answering that question. So let's work on understanding the concept, not only because of the concept's sake, but because these kinds of quantities are going to come up again and again and again. If you want to understand density, I mean really understand it, you have to understand three things. You need to understand what we mean when we talk about the mass of an object, perhaps measured in units of grams. You need to understand what we are talking about when we talk about the volume of an object, perhaps measured in units of cubic centimeters. And lastly, you must understand what we mean when we talk about mass per volume. What do we mean when we say grams per cubic centimeter, which may be represented in a few different ways as shown on the screen? And that's what we're going to work on for the next several minutes. Let's take a look at mass. And in deference to the physicists and physics teachers, I probably should say this. Physicists are very careful about distinguishing between the terms mass and weight. Mass is the amount of material, the amount of matter in an object. For example, if I take an object like this, there's a certain amount of matter in here. It has a certain mass. And if I take this object to the moon, it still has the same amount of matter. It still has the same mass. But if I weigh this object on Earth and weigh it on the moon, the weights are different. Because weight depends on the attraction of gravity. And on the moon, the gravitational attraction for an object is something like 1/6 of what it is on Earth. So while the mass of this object would be the same on the moon as it is on Earth, its weight would only be about 1/6 as much. If you've ever seen pictures of astronauts on the moon, that's why they can jump, even though they're wearing those bulky spacesuits, and why they come down so slowly. It's because gravity isn't acting so strongly on them. Making a distinction between the terms mass and weight is probably technically important, so please be aware that there is a technical difference. On the few occasions that I taught physics, I certainly emphasized the difference. That said, I will tend to use the two terms interchangeably in this entire lecture series. And so long as we don't travel away from the Earth, which I really don't have any intention of doing, the difference really won't make any difference in anything that we're going to do. I will prefer to use the term mass when talking about the grams of something, but I may slip and use the term weight, and that's probably of no great importance. Now, how do you develop a real understanding of the concept of mass? That's a very interesting question. How do you develop good insight about what is meant by the term grams? You've heard it. You may even be able to give me a definition. Students like definitions. Definitions make for common test questions. What is the definition of a gram? A gram is the mass of 1 cubic centimeter of water at the point of maximum density. Well, I mean, that's nice, and it's certainly true. But does your ability to parrot back this definition mean that you understand what a gram is? Does this mean that you really have any feeling for what a gram is? Of course not. You've just memorized a definition. You may very well understand what a gram actually is, but just being able to give the definition doesn't prove that you do. Here's how you get to have a gut feeling for what a gram really is. This is how you make the concept like mass real. Let's begin by taking a nickel. A nickel is worth 5 cents. And if we put a nickel in our hand and close our eyes, we can sense its weight. We'll call that its mass. By coincidence, a nickel happens to have a mass very close to 5 grams. Now, please don't extrapolate from this. I mean, dimes don't weigh 10 grams and quarters don't weigh 25 grams or anything like that. This is just a coincidence. I want you, when you get a chance, to hold a nickel in your hand. Hold the nickel. That's 5 grams. Get a sense of that. Weigh it on a balance in your chemistry class if you can. Then hold a different object. Try to estimate its mass. You know, at first this can be quite difficult. Hold lighter objects, hold heavier objects. Try to get a feeling for what their mass is. Then weigh the objects on a chemical balance at school if you can. If you don't have access to a chemical balance, perhaps you can use a scale that's used to weigh food. After a time, you should truly be able to have a real good feeling for what we're talking about when we say that an object has a mass of 34.59 grams, for example. After a while, this becomes a truly meaningful, intuitive concept to you, not just some meaningless unit that's attached to a number. We actually do this in class, and it's fun. It's fun to see who is naturally best at this. Despite my experience, there will usually be one or two students who will beat me fairly consistently, and of course that gives all my students, great pleasure to see. Developing a feeling for what this or other things really represent is something that happens so subtly, you may hardly be aware that it's happening. But when you develop this intuitive understanding, it's going to help you throughout the entire course. When you're reading a problem, and it says that an object has a mass of 34.85 grams, that quantity becomes more than just an almost meaningless number. It becomes real to you, just like 3,000 students is a real thing to you. What about volume? What does that represent? Volume is the amount of space taken up by an object. Now try not to confuse volume with mass. Volume has to do with the size, the amount of space that something occupies, not the amount of matter that it contains. One common unit of volume is the cubic centimeter. And the cubic centimeter is easily defined. It's simply the volume occupied by a cube whose sides are all 1 centimeter in length. On the screen, you see a representation of a cubic centimeter. If you remember your geometry, the volume of a cube is just the product of its 3 dimensions. So the volume of this representation is 1 centimeter times 1 centimeter times 1 centimeter, or the volume equals 1 centimeter quantity cubed, or 1 cubic centimeter. In 3 dimensions, to scale, this is a cubic centimeter. Look at that. Burn it into your mind. See how big that is relative to my hand? That is a cubic centimeter. Hopefully, over the last few minutes, some changes have occurred. A few minutes ago, the term cubic centimeter may have been just an almost meaningless term. Now it should be something that you can actually visualize in your mind. Now what you need to do is take objects and try to guess their volume. If they have a nice, regular shape, like this object, after you guess how many cubic centimeters this might be, you can measure the dimensions, in this case multiply the length by the width times the depth, and compare the calculated volume to your estimate. If the object were, let's just say, a cylinder, you can do the same thing if you know, or you can look up the formula for calculating the volume of a cylinder. I'll bet you already have a good estimate of the volume of this cylinder in cubic centimeters. Is it more or less than 1 cubic centimeter? I suspect you know it's more. Did you know that 10 minutes ago? Well, I mean, perhaps you did, but if you didn't, I think you do now. Is it more than 2 cubic centimeters? 3 cubic centimeters? 4? 5? The important thing is not that you estimate the volume with great accuracy, but when a problem says something has a volume of perhaps 22.7 cubic centimeters, you have at least some understanding of what this really means. But